So welcome to lecture 31 of MCS 471 on numerical analysis, and today in particular on solving initial value problems. Initial value problems are actually quite difficult. So we will introduce the notion of stability of a method, in particular of Euler's method, and we will introduce another variation of Euler's method. We will end with the backward Euler method, which will prove to be superior to the Runge-Kutta methods that we have covered earlier. So, and I will start with the Runge-Kutta methods, which are typically used in an embedded fashion. So what we will get to is the step size control. So we have so far assumed that we will, as we discretize an equation, that we will use the same constant h throughout the entire trajectory. Now, fine for many examples, but this is actually not so much fine in practice. And speaking of practice, we will use the RK45 of the integrate module of SciPy, available within the computational ecosystem of both Python and Julia. All right. Step size control. What's the problem? Well, let's start from the beginning again. We have an initial value problem, and there is no, for our examples, our test equations, there are explicit solutions, but in most applications, there is not an explicit solution. So what we are doing is that we are approximating the solution. So we are putting points that are approximating a function. So we have Runge-Kutta methods. P-stage Runge-Kutta uses function evaluations and has a global error of h to the power p. So there is a big O there, so the constant matters in this course. But this is the expected behavior. So we will see that in practice, this is a good rule of thumb. So if you use a fourth order Runge-Kutta method with a step size of 10 to the power minus 2, then we may expect 8 decimal places accuracy. That is good to begin with, but that's not everything. Some trajectories may be harder than others, and actually some problems are harder than others. But let's not rush. Let's first answer the question, and let's do the question here: how to choose the step size. So this is for some h, and what we do is we try and we see what comes out, or we have these orders that are kind of the expected values for the errors. But can we do something better? Can we estimate the error? It will turn out that the answer is yes, so we will solve this problem. All right, Euler and the modification. Here is the idea. So when we run Euler's method, as we have seen, we truncate the Taylor series after 2 terms. We have Euler's method. That's not accurate enough. We then use some averaging, get the trapezoidal rule. Then actually, if you consider the overlined next approximation and subtract from that the new approximation, then actually we do have an error estimate. If you remember in our experiments too, the local error of Euler's method is actually not that bad. It's h to the power 2. So, and the local error remains kind of because the modified Euler method has a global error of 10 to the power of h to the 3 is cubic in h. All right, so here is then the step size control. The controlling of the step size here is an algorithm that will cut the step size in half if the difference between what Euler and the modified Euler gives you is too large. It could also become too small, and then you double the step size. So that's it. So that is an adaptive step size control that you could do with Euler and the modified Euler method. There is, however, a problem to that. While good of an idea, the Euler method itself is often too inaccurate, and we will propose and we will see higher order. We will apply higher order methods in pairs. So what comes after trapezoidal rule? Simpson's rule. So let me introduce the idea referring back to numerical integration. Here is the trapezoidal rule. Its name is obvious, for the area of the trapezoid is the approximation of the area under the blue curve. What comes next? Well, we have Simpson's rule. With Simpson, you construct a parabola through 3 points, the endpoints, and then the midpoint. So this is another presentation of Simpson's rule. We can see Simpson's rule as the trapezoidal rule with one more point. We recycle one function evaluation. So, and the Simpson rule here gives the area under the blue, under the green parabola as the approximation for the area under the blue curve. All right. Here then you see the idea. How can we now use the Simpson rule to estimate the error of the trapezoidal? Well, we do one more point and we compute the contribution of the rule of the Simpson rule. So in a way, we are doing one extra function evaluation. So the previous function evaluations are weighted less, so they have the weight 2/6. The new function evaluation has a higher weight, 4/6. So the new function evaluation, if you like, counts for twice old function evaluations. So we've seen the composite trapezoidal rule. One can also make now a hybrid with trapezoidal and Simpson by just taking one extra function evaluation in places where it matters. So we have not addressed fully well adaptive integration, but this is the idea that we're going to apply from quadrature rules. Because the modified Euler method is actually the trapezoidal rule. All right, let's now work out this idea in the setting of Runge-Kutta methods. So what are Runge-Kutta methods again? So let's first make the connection algebraically or with the calculus. When we derive our methods, we can do numerical differentiation or we can do numerical integration. Here we apply numerical integration. We derive the trapezoidal rule by applying the trapezoidal rule to the right-hand side. we apply the Simpson rule by applying the Simpson rule to the right-hand side. Note that the h here is the size of the interval. All right, we have the function values at the beginning and at the end, and then one extra function evaluation in the middle. So, and the point is that that one extra function evaluation estimates the error. All right, let's now see how this gets applied in the context of a three-stage Runge-Kutta method. A three-stage Runge-Kutta method which will use one extra function evaluation. So we are applying the Taylor series, and then the way we designed our Runge-Kutta methods is by identifying the rule, the coefficient, the parameters in the rule with the coefficients in the Taylor series. So we do the Taylor series. We want to have at the first three terms. So we want an order 3 method. So we want to go one step farther, and then we apply forward differences onto the second to approximate the second derivative. All right, where is this going to? Well, let's see how we can get a midpoint there. So we simplifying our expressions. So here we see the factor h over 4 coming in. I should have pointed this out on the previous slide, how the h to the power 4 arises. We find actually an expression for the midpoint, for the value, for the function value at the midpoint. So the function value where we take xn plus half of the interval, and also we evaluate y at xn plus the half of the interval. Why is that now useful? Because we can write this as this expression, but I will mark here. This expression we can now write in terms of the earlier function evaluations k1 and k2. K1 being used in the in the modified Euler method. So the modified Euler method uses K1 and K2. So we have these two function evaluations which are used. So these are not the same, but these are used. So this is actually not an identification, but with the labels here, I want to indicate that we are looking for recycling the function evaluations. So our rewriting, so let me back up now a little bit. The rewriting was necessary because we cannot really find why. We cannot write the expression that is over here. So y is the unknown function that we're looking for. So we want to rewrite this unknown y at the middle using the Taylor series expansions and using the function values that we have already computed. So in some sense, it's an interpolation as well. It's a weighting of previous function values for the point at the middle, for the function value at the middle. So we find that we have actually now the identification that the value of the unknown function in the extra point at the middle is the yn, the approximation that we have already, and h over 4 with the two k1 and k2. All right, let's summarize. So the application of the Simpson's rule can now be reformulated as a three-stage Runge-Kutta method. So the first two stages are the modified Euler. So K1 and K2 are what is used in the modified Euler, so that will be important in what follows. But what we have just arrived, and perhaps I should emphasize this again, we have just arrived, derived the rule to replace the value of the unknown function y at the midpoint. So this gives us a three-stage Runge-Kutta method. Why is it a three-stage Runge-Kutta method? Well, we use three function evaluations. And what is important here is that the error is, the global error will be of third order. So these are the properties of Runge-Kutta rules of p stages, of three stages. Fine, we have another three-stage Runge-Kutta method. You could also call it Simpson's method. How are we going to use this now? Remember our original problem. We want an adaptive step size, but the Euler method is not accurate enough. So we will actually using now the two-stage Runge-Kutta method, the modified Euler, to give our first guess. And the three-stage Runge-Kutta method that is presented here will be used to estimate the error. Here it is. This is our embedded Runge-Kutta pair of order 2 and order 3. So the order 2 means that the local error is of third order. So we have h to the power 3 locally. And that is already, for many examples, accurate enough. So we are going to go one order higher. So the local order of a three-stage Runge-Kutta is h to the power 4. So we have fourth order. But here now you see the rule, or if you like, the program, where we are going to apply the weighting of the function evaluations. We're going to weight them twice. Once according to the trapezoidal rule, and once according to the Simpson's rule. And we have an error estimate by subtracting. So the error estimate is the difference of what the modified Euler method gives us with the three-stage Runge-Kutta pair. All right, how does it now done in practice? So in practice, the most popular rules are actually one order higher. So these, even the writing down of the complete formulas, you can look up textbook. They don't say that much. Well, they are long, and the derivation is also complicated. But what is actually most important is that there is very good software available. So in the SciPy package, the integrate module has the RK45. And I think rather than looking at the formulas for the 4 or 5 embedded pairs, we will look at how to use them. Here it is. So we will test this out. So the the application of the RK45 requires a right-hand side, so it's working on a system of differential of right-hand of first-order differential equations. So here our test function, the right-hand side is just y. So we define the test function. So this is valid, Julia, by the way. We give the test function the start value, so it's still an initial value problem. So the first number here is the T naught, which is by default always 0, but you have to specify it. And then we have the initial conditions. We have to present them as a tuple, but we have y naught here. So this RK45 works for functions, for systems of first order differential equations. Then the third numerical parameter is the end time. So we sometimes call this the capital T for the simulation interval from 0 to 1. Now, it is an adaptive step size control. We can give the relative tolerance as a parameter. So here we want 7 or 8 decimal places accuracy. So we give that as the parameter. So what this does, it defines a function. So if you like, it defines an iterator. So you can step on that, and the step will change the status. If we have reached the end, the status will be finished. And here you see that the RK45 on the test equation is actually quite efficient. In 6 steps, we get the approximation for E. So I should probably also have printed out the actual value, but you can see the error is up to 7 decimal places correct. So by the way, this is also an illustration of why you want adaptive step size. The step sizes can sometimes be quite large. So by default, our largest step size was 1/10. So here you can see that we don't need 10 steps if we are satisfied with 8 decimal places. If we are going to use Runge-Kutta methods in practice, and now I'm thinking about a course in industrial mathematics, then we will use it in this way. So we will use the software that is standardly available to us. All right, excellent. But it's not done yet. Let's now look at the problem of the conditioning again. So we will consider an initial value problem. So we defined the numerical conditioning of the problem as the dependence on, as the sensitivity of the initial condition. So again, for our test problem, we have an exponential there, but notice that the x, actually the end value for x is typically 1. So what we have is we have a condition number that is actually very good. So it's 2 something. So the dependency on the initial value problem should actually not worry us that much. So the test equation is well conditioned. Well, let's examine that a little bit farther. So here, what does the solution look like? For positive values of lambda, we are having an exponential growth, and that's why we are restricting to 1. We may actually also have oscillating behaviors if the lambda is complex. So here the real part means the RE means the real part, but we have if we have an imaginary part that is different from zero, then we have cosines and sines coming in. So in a way, this problem looks a lot more interesting now when we look at complex numbers. But we have already addressed this when we considered higher order differential equations. Periodic orbits appear very naturally with second order equations. But we will focus today on what happens with the exponential decay. We can take still real values, so we will not consider complex values, but we will consider small values, exponential decay. So in what follows, we will look what happens in the case where we have a decaying solution. The numerical conditioning is fine. We have then E times some negative power. So our condition number actually, the sensitivity on our initial problem, in initial condition is actually great. However, the solution is decaying. And that will impose a condition on the step size for the method to be stable. Let's examine that a little bit closer with doing some experiments. Let's consider Euler's method again. Euler's method was very simple to define, very simple to execute, because we have explicit formulas. So here we have this explicit formula for Euler's method. 1 plus lambda times h. Now notice if the lambda is negative, our solution decays, and we can derive a condition on the value of h, because what we want is also that the approximations become smaller and smaller. And we can compute how small they are going to get if and only if we have this condition here, so which is a translation of the factor that you multiply. So yn plus 1, the next approximation, is 1 plus lambda h times the previous approximation. So we have that the 1 plus h lambda, so lambda is a constant here. You cannot choose this. That's given by the problem. What you have to determine is a value on the step size. All right. What is the problem now? So we have a condition. So with Euler's method, when lambda was 1 and we wanted 6 decimal places, then we needed 1 million function evaluations. Pretty bad. And that was already bad. But it can always get worse. So if you take lambda minus 10 to the power minus 6, then your step size, you also need 1 million function evaluations. Otherwise, you will diverge. I mean, you will not even converge anymore. So forget about having any accuracy. So that's quite dramatic here. So in this course, we have seen a lot of dramatic calculations, but here is another experiment that runs entirely wrong. So we have a negative value for lambda. So our exact function is, so the exact answer is exponentially decaying, but our approximations do exactly the opposite. In 10 steps, we have no accuracy left anymore. All right, let us try to improve this. It can also get oscillating. So here is another example. When we cut the step size in half, so we go from 10 steps to 20 steps. Here we see the result. We have 1 and -1. So one may think that the solution is oscillating, but it is not. So also this is a very bad, and it turns out that you need to take the step size. If you take 1/30, then actually the solutions decay. All right, the first exercise, experience this for yourself. So we have a deep distrust now for Euler's method. Let us do this for even smaller h, and explain what is happening, looking at the formula of Euler's method. So in solving this exercise, you will run the code that is posted, or you can take the code from a previous lecture. And then the second part of the exercise, you will use the explicit formula to explain the observations. So Euler's method gives an explicit formula for the values. All right, let us dwell a little bit further on this. So with Euler's method, we needed a very small step size, and the step size was depending on the value of lambda. Is this the case for the modified Euler method? Well, let's check. With the modified Euler method, we can also do the same reasoning. We can find explicit relationship. So the modified Euler method is an implicit method in some sense. So remember the problem that we had, why we needed the extra step, because the yn plus 1 occurs both at the left and the right. But with a simple test function, we can still simplify. So we can actually see that the next function, the next approximation, if the previous value multiplied with some ratio. And here you see the ratio involves h and lambda. And the relationship between h and lambda is actually now quite a good one. So here we have this condition here. If this is satisfied, then the method will be stable. Here this is elaborated or worked out in greater detail. We are working on the assumption of exponential decay, and we are manipulating these inequalities, and we see that if we manipulate this right, that for exponentially decaying solutions, there is no condition on lambda, on the h. So the positivity of h automatically satisfies the condition. So the modified Euler method is actually on exponentially decaying problems unconditionally stable. All right, so let's run the modified Euler method. And now actually we see that the solution is decaying. So the method is stable, but however, you see that it's not good. So we are having a very, very slow decay. All right, let's continue this. The exercise asks you to verify this, running the modified Euler method on this problem, explaining what you observe, describe your observations, and also use the formulas. Now, what is interesting here is what is the really largest value you can be considering. So the fact of unconditional stability, does this actually work? So note that okay, so here is, I have to explain what is the purpose of this exercise now. This exercise, the problem is that we run it in the predict correct format. So in the previous experiments, we ran this, we were thinking of the explicit formula. So notice that you can run, so I probably should have emphasized this here. Why is this exercise still important? Because this is a formula which is derived for the test equation based on the modified Euler method. So it is indeed a version of the modified Euler method, but it is a different formula. So it's a different program. It's used in a different format. This exercise now asks you to run the two-stage Runge-Kutta format of the modified Euler or the predict correct format of the modified Euler. So it is a different formula. And note that the Euler method actually does diverge. The point is, can you actually run the modified Euler method in the predict correct format with 10 steps? All right, let us continue this. So I still have about 10 minutes in this lecture. We can generalize the behavior for our methods, and we will classify the problems we will define a new class of problems. But let us first now define what is. So it turns out that we try to phrase numerical analysis things with conditioning and stability, numerical stability. But here we have also stability of solutions. So it's a property of the solution now. We say that the solution to a differential equation or to an initial value problem is stable if we have this definition of continuity. We can make that any approximation is as small as we like by picking our initial values appropriately close. The way to read this definition is that we have an epsilon. So we want that at the end of time, we want to have a certain accuracy. Then the solution is stable if you can realize this by taking the initial conditions sufficiently close to each other. And the delta, the smallest the delta we can get is the machine precision. We say that, so it is asymptotically stable if we can do this for the end of time. So the axis here seems to suggest space, but it also is time. So there is no, so we can go asymptotically. And this property applies only for stable. All right, we then have another definition. So the stiff equation. So we have seen an example actually of a first stiff equation. So we have that the initial value problem is called stiff if we have a step size that must be so much smaller than what you may expect from the method. So the Euler method is actually order h in accuracy, global error. But you need, so if we need 6 decimal places, then we need 1 million function evaluations at one. But if you have a problem that is stiff, the step size needs to be a lot less. So this is explained here in words one more time. So you expect that with Euler's method, the number of decimal places is proportional to the accuracy requirement. So your step size is inverse proportional, direct inverse proportional to the accuracy. Or if the accuracy has to go up, the number of steps also has to go up. So with 1 decimal place of accuracy, you must do 10 more steps. So that's why Euler's method is kind of a benchmark, the measure that we use here. All right, here is our last example. So it is an initial value problem that is more simple. Well, you see still there is the minus 10 times y that comes in. But it is not an exponentially decaying, it's an exponentially converging method. So perhaps I should show the plot here. So in a way, so by the way, this plot is also sometimes used in a model for a learning curve. So you can kind of see if between 0 and 1, how much effort do you need to spend, and you get 50%, you start at 50%, but then how much more effort would you need to get 70% to get 80%? So how steep is the learning curve? All right, so it is rapidly converging, but if you use the RK45, that used only 6 steps on the test equation. Remember, here actually on this relatively simple method, you actually need 320 steps. So on this simple, rapidly converging solution, you actually need so many steps. So it is an example of a stiff equation. How to do this? What to do about this now? Well, in order to solve this better than the RK45, we need to use an implicit method. So this is another class of methods. We will introduce it with Euler. We will see more examples of implicit methods later. So the backward Euler method, so the forward Euler method, which was simply Euler's method, uses the function value at the current step, looking forward. So you could see this also as a forward difference. The backward Euler method uses the function evaluation at the next step, which is kind of absurd because you can't do this because, again, you have the problem that if you want to evaluate this formula, you have something that is at the left and at the right. And what is at the left is what you want to compute. And it's kind of a recursion. And that's why it's called an implicit method. Now we will see how to use implicit methods in conjunction with an explicit method. So that will be the topic of next lecture, where we will consider predictor-corrector methods. But we can already apply it on this problem here, where we will, for this particular problem, where we can regroup, where we can reformulate the method. So we can reformulate the right-hand side. We can use the particular format of the right-hand side to derive an explicit formula. So, and we will use that explicit formula here where we to execute the method. So it will work for the specific problem that we have, and here is how it is working. You can see that we have the exact solution, so we can compute the exact error. And we see that we are converging extremely well. So with 10 steps, fixed step size here, our approximations get better and better. So the backward Euler method is stable. And that will be left off as the last exercise. So the stability of this method is first to formulate the condition of the stability. So you have here also, it will be a reformulation. So we have that the error, we have that the value in the next step, so the y of n plus 1, can be written as something. I will put the something here between brackets and the yn. So, and you can kind of see already what it is. So you have the factor 1 over 1 plus 10h that comes in here. So essentially you have to factor out to present this in a factored form. And the condition of the stability is that whatever comes here is actually less than 1. And you will see that there is no condition on h. So the method is actually stable for any positive value of h. So that you can see also on the formula. We will divide in the denominator for any positive value of h. You have a denominator that is larger than 1. So the condition is actually satisfied. All right, I will close here. So we will continue with this next time on predictor corrector method.